It's going to be one of two talks on Carmes, next one by Andreas. My plan is to describe the instrument and to describe a little bit the science case and the first 9 months of operation since January 1st, 2016, this year. So let me start with the science case of the instrument. The science case is just a very simple and straightforward one, is to search for Earth-like habitable planets around low mass stars, M dwarfs, and preferentially very late M dwarfs, as late as possible. And the reason for that is for a number of things. Understand their statistics and formation mechanisms by building a large sample, understanding their precise properties and habitability, and also perhaps finding some treasure systems, some very, very important systems that we can further characterize and understand beyond the observations from Carmenes and with Carmenes itself. So the Carmenes GTO, the survey, is a survey of 300 M dwarfs. That is, they are observed simultaneously in visible light and infrared light, and this is the big plus of Carmenes, as you will see in a second. This is is now currently installed at the 3.5 meter telescope in Alto, and according to an agreement, at least 600 useful, in quotes, whatever that means, nights have been guaranteed to Carmenes, and up to 750 depending on the results that we obtain. And as I said at the beginning, the survey has been ongoing. The instrument was commissioned late last year, and the survey has been ongoing since January 1st this year. So we spoke of niches this morning. This is the Carmenes niche. Carmenes niche, this is exoplanets known today, not today, but on May. And as you see, this is mass of the host star, and this is mass of the planet. Low mass planets down here, high mass planets up there. The Earth sample is here, and Jupiter is sample is there. And this is the host star mass, and there's lots of planets known for around sun-like stars. So that we have plenty of statistics here, thanks to the radiolocity surveys and also to Kepler. But the number of planets around low mass stars, this colored part would be the M dwarfs, and the darker color is actually the late M dwarfs, M3s and later. So the statistics that we have here is still quite scarce. And the idea is to increase this number by at least a factor of 2 or 3 with Carmenes, and then to understand all these questions that I was mentioning at the beginning. One important thing for Carmenes is what I said about habitability. So we care about habitable zone planets, so planets that are at a distance of their star that is at which the planets are able to sustain liquid water on the surface. And this would be this classical habitable zone planet. Stellar mass here, orbital distance there. This shaded region is this habitable zone, and the M dwarfs are this part here. And as you can see, these are the limiting detector limits for planets of these sizes. So we can detect all the planets to the left of this line, and if we can do 1 meter per second or so radial velocities, that means that we can probe the habitable zone of these M dwarfs for Earth or super Earth-like planets. The nice addition to that as well is that when we look at the typical orbital period of planets inside the habitable zone, for a 0.4 solar mass star, this would be about a month, and even for lower mass objects that are actually less, so in 10-15 days or so you cover the entire orbit of this planet inside the habitable zone of these very small stars. So that's the second addition to the opportunity, the fact that the time goes fast, let's say, in terms of building orbits. So with this idea in mind, the Carmenes Consortium was set up, and this is 11 institutions, 5 from Spain, 5 from Germany, and an additional one is Calar Alto, and these are all these 11 institutes. There's a system in which we have a PI sitting in Landessternwarte in Heidelberg, and that's Andreas Kurenbach, and a deputy PI who's from the IAA, that's Pedro Amado. And then we have also 2 project scientists. One is myself in Barcelona, and the other one is Ansgar Reiners in Göttingen. So, the Carmenes instrument, the acronym is no way, right? Calar Alto High Resolution Search for M dwarfs with exo-Earth with near-infrared and optical shell spectrographs. And one very important thing about Carmenes is that it's a single-purpose instrument. The instrument is being built to detect planets of this kind, and it's also highly stabilized to be able to make that a reality. It has a wide wavelength coverage, I said, from the visible to near infrared. That's from 0.5 micron all the way to 1.7 micron. And the idea for that is that 2 reasons. One is that M doors emit the bulk of their radiation at about 1 micron or so, so we want to cover that area. And the second reason is that there is a plethora of false positives that can affect the detection of a planet. The worst of these false positives is caused by stellar activity, and stellar activity has a chromatic signal, meaning that the amplitude of these radial velocity variations will change as a function of wavelength, and therefore this wavelength, such a wide wavelength coverage, can allow us to discard these false positives from real Keplerian motions by planets. So the characteristics of the different channels, there have been both built to attain a precision of 1 meter per second or so. Our benchmark integration time is SNR of 150 at J equals 9 in 15 minutes. And so this would be what we can do in the infrared. Similar thing with the visible channel. As I said, the vis channel from 500 nanometers to about a micron, the infrared from 1 micron to 1.7 with resolutions of 80 to 90,000 or so. Both are in vacuum, stabilized at different temperatures. The vis channel is stabilized at ambient temperature, while the infrared, because of radiation issues, is stabilized at 140 K. We have a mosaic of MCT Hawaii 2RGs with an infrared and 4K by 4K CCD E2V. And there's also a very important factor to acquiring high precision radio velocities is that the fact that we need stabilized light source that we can calibrate against and correct for drifts from the spectrograph. And in an infrared we have uranium neon lamp, and the visible channel we use these hollow cathode lamps, thorium argon, uranium neon, and uranium argon, plus an etalon, Fabry-Perot etalon, to provide calibration of this drift during the course of the night. So we use this for baseline, these hollow cathode lamps, and then we have nightly corrections to this simultaneous calibration with this etalon. CARMES is a fairly complex system. It has 2 vacuum tanks, the visible spectrograph and the infrared spectrograph, a number of systems attached to it, and then of course a front end that is also shared with PIMAS. And this is the number of systems that we've been developing over the years. So I'll show you a few pictures now. So this picture is actually about PIMAS. But we have here the CARMES front end, and there's a mirror that lets light through PIMAS or sends light off to the fiber inputs from the CARMES spectrograph. This is the optical bench of an infrared spectrograph with all the different components just before integration and assembly. This is the infrared vacuum tank once assembled. The idea is that we close these and we don't open these in years, right? Because the system has to be stabilized a very long time, of a time scale of years at least. This is, as I said, there's the calibration units. These are important factors. These are the lamp calibration units, and this is the Fabry-Perot. There's still, while it was being installed, that's hence the hoses and everything. Now it's much cleaner, let's say. And this is injecting light into the calibration unit and up the telescope and down to the spectrograph. There's also a very nice system that's been fully developed in Calar Alto, thanks to Jens here. And that's the so-called interlock system that is it's in charge of controlling and acting upon the pumps, bulbs, and all the different things that we have to take care of up there. It has a very nice touch screen that you can go and play with when Jens is not around. Also, another piece of important equipment here is the ICS, the Instrument Control System. It's also is a complex machine, many different subsystems, and so we have a brain of instrument. This is this instrument control system that is also has a GUI for people for observers to interact with and to acquire observations and so on. So here's some CARMES data, and this is a full spectrum. The BIS channel spectrum is here. This is the CCD. 55 orders covering the set wavelength range, and this is an infrared part, 28 orders coming from 1 to 1.7 microns. So this is actual data. And again, this is one order at 800 nanometers. This is BIS channel, and this is the comparison of the star spectrum plus this Fabry-Perot light that we're using for calibration for stability checking of the radio velocity solution. So we take, at the same time, we take a spectrum of the star and a spectrum of the etalon, and then we can check drifts in radio velocities. So this would be a full spectrum of a target from, as I say, from the visible channel and the infrared channel. You see lots of features here. There's some emission features from skylines, and there's a lot of absorption lines also from the sky, and of course the infrared is very thick in absorption features from water vapor, but this we have techniques to remove, and we're doing this routinely. So as coming back to the start, the primary science objective is to carry out a survey of 300 stars, main sequence stars, late M's, and to try and find a number of them in their habitable zones, and potentially a few that will be transiting. And this, again, this would enable a lot of characterization for these guys. We focus on as late as possible M dwarfs, and we can also handle stars that are slightly active because of these bis plus near capabilities that we have. So the idea is that we would be, with the setup, we would be able to detect the 2 Earth mass planet in the habitable zone of an M5 star, which is about 0.12 or so solar masses. The other thing is that we are dealing with very nearby stars. So all these stars are within several parsecs, actually. I'll see in a second. So we selected 300 stars targets because we want to build enough statistics to understand planet formation, as I was saying, as a function of different parameters. There's high chances of having at least one transiting planet because of geometric probability. And essentially, we include most of the targets, if not all the targets, that we can yield good SNR, good signal-to-noise ratio, being late M's, let's say. And we aimed at about 60 measurements on average per target. And we have divided our target list up in 3 different sub-samples of 100 stars each, to fully, let's say, to make use of time at which the conditions, the conditions on Calar are not so great. So we have some bright objects that are early spectral type, and then for the best nights we focus on the very late objects that have usually fainter magnitudes. So this is the current Carmenes sample, about 300 stars. Mean distance is 13 parsecs, and as you see, we have different magnitude cuts as a function of the spectral type. And you can, on average, our sample, our main target, is about a J magnitude of 8 or so, and spectral type M3, M4. This would be the fiducial Carmenes target that we are observing. We have carried out a number of simulations on what will Carmenes detect, and this is a paper that is now undergoing refereeing process. And our conclusion that, of course, it will depend very much on our ability to separate false positives from real signals. Worst case scenario is that we'll detect maybe 25 to 30 planets. Best case scenario, maybe 100. So that will depend on how well we do in these corrections. Of course, it's a lot easier to detect. This is our plot from this paper. This number of planets as a function of radial velocity amplitude of the light curve, for semi-amplitude, and for different shades of color mean different cuts, let's say. And the easiest one, let's say this green one would be detecting almost everything above 5 meters per second or so. And this is, again, these 25 to 30 objects. And as I said before, we are sensitive to super Earth type planets. So planets that are above 2 Earth masses or so, and all the way up to the Jupiter mass, although they're quite scarce. So I promised talking about the 9 months that that have been elapsed so far in the GTO program, the survey. We have obtained about 2,500 measurements total in the invisible light and infrared measurements of target stars. We have observed almost all targets already, 300 of them, because we have taken the compromise of delivering one spectrum for each target at the end of this year, actually, and this will be published and will be made public for anyone to analyze. We have 3 targets with more than 100 observations, 15 with between 100 and 30. We have about 10 observations per star on average, and we have acquired observations on 160 nights, but this is not full nights. Some of these nights were not completely usable in full, let's say, and so of equivalent time, this would be maybe 100 or 120 nights or so, so far. Okay, and here's some results already. This is where we stand now. This is RV standard deviation, and as a function of number of radial velocities. And these are, of course, you can see some objects that have very, very high standard deviations here. And these are objects that are very active or quite active. We will throw them away probably, or at least monitor them for a little while longer. And there's a bulk of objects that have RV variations of 10 meters per second closely or above or below. So it means that at least we can see that there's objects with many observations that have very low RMS values. So they either have low mass planets or maybe no planets, but at least that proves that we can acquire long time series with enough precision. Would be nice to say this is the first Carmenes planet. No, it's not. This is a planet that is already well known. This is GJ436 that was discovered back in 2007 or 8, I believe. So, and this is one of the highest amplitude low mass planets around, let's say, highest amplitude planets around low mass stars. And this is a Neptune-sized planet around an M3.5 star, which, as you see, has an amplitude of about 20 meters per second. We detect this very nicely with Carmenes data. There's no doubt that this planet stands out very immediately. And we have a standard deviation of these measurements. These are, by the way, measurements from the visible light channel only. And the RMS is 2.5 meters per second or so, which I have to say includes instrument effects and stellar jitter. So jitter is also there. And those stars are shaky because of this activity issue. So we're in good shape, and actually probably the parameters that will follow from the analysis of this will be actually of better precision than those published so far. Another plot. This is the frequency of a standard of different of the RB standard deviation. Our median is 4 meters per second in this, again, the visible channel, and this is quite similar to the median of M-dwarf surveys obtained with HARPS, which is this instrument that's been ongoing for years from the southern hemisphere. So, but again, this 4 meters per second includes instrument effects, astrophysical jitter, and in this case also includes planets. So there are some planets in our sample that are increasing this jitter, of course. And these would be candidates. So no names, of course, because you could take pictures and go and observe them with some instrument. But these are objects that only with a few measurements, not so many, they're starting to show periodicities that are indicative of something going on. Some may be, he's taking a picture, but he's not from the team though. Some may be actually activity issues, or some may be other things, but some may be planets already, so maybe these will not end up being planets, some will, but at least we're having some signals that we're tracking these days. We've discovered some things that are already very well determined, things that we're not after, but this is a new M3 spectroscopic binary. So these are two binaries of M3 type, so probably low mass of 0.3 solar masses or so, that are not so numerous. Unfortunately, this one is not eclipsing, and therefore is not so interesting, but this came out of right away from our analysis, because I can see up there, radial velocity signal is of the order of 60 kilometers per second, and this is really a piece of cake for Carmenes. So besides the main survey, Carmenes is also very useful to do additional science. The consortium ourselves is interested in additional science, and also, as you know, Carmenes is offered to the community, and there's open time through both normal Calar Alto time and also through Opticon. And there's been, I won't be discussing this, but there's lots of proposals and a lot of interest on using Carmenes to address stellar atmospheres, stellar activity, binary systems, eclipsement or not, planetary atmospheres. This is challenging here, using Carmenes to do a diagnostics using atomic features, evolved stars, AGBs and so on, searching for protoplanets with an infrared channel capabilities, observing planetary nebulae, and a whole lot of different things that are happening right now. So, just summarizing what I said, and this is just setting the stage for Andreas' talk next. Carmenes is already well underway in its aim of detecting habitable planets around very late M-dwarfs. We started regular operations about 9 months ago, and we expect at least to go at least beyond to the end of 2018, maybe beyond, if Andreas is successful convincing you guys. Both channels are online and they're acquiring data. I showed only this channel data though, because the infrared channel we're still working on. Actually, it's not true. I showed data from the infrared channel as well, spectra, but the stability, radial velocity stability is still not completely under control. We have in the infrared stability that is of the order of a few meters per second over a time scale of one night, but the long-term stability of the infrared channel is still not completely under control, and we're running campaigns now. In the case of the visible channel, I have shown you observations that prove that we have stability of the order of 2 to 4 meters per second for sure, because we see objects with long time series that show this kind of statistical effect. And of course, this is still including instrument calibration and activity jitter. And as always in any of these instruments, because this is also happening with HARPS today, which has been online for at least 12, 13 years, we are working to improve the precision and the time scale and the time scale of this stability. We are working hard on fine-tuning the pipeline, the reduction pipeline, which is also a very important part of the entire project. And at some point, we are reprocessing everything once and again and improving on the radial velocities. So I think the takeaway message is that Carmen is up and running, operational, and hopefully we should have announcements of planet detection soon. And also you're very welcome to use it actually as an instrument that is now currently available on Calar Alto. So thank you very much.
You mentioned you could in principle remove signatures of stellar activities from your data. Did you already try to do this?
We have, let's say, not with real data yet because the infrared time series is still not available, but we've been running lots of simulations with the stellar simulation that we have now up and running, and the theory says that it's possible, but it's not as straightforward as we thought, because there's a phase lag between the infrared and the visible light RV signatures, let's say. But we're coming up with good ways of doing that. But it's not going to be let's say, very straightforward.
But this could improve significantly the precision.
Absolutely. That's the idea. So in all these simulations we've made, we are assuming a pessimistic amount of value of the stellar jitter. We have been doing some research with HARPS, and the jitter for mid to early M's is of the order of 3 meters per second when you don't do anything. So by having the visible and the infrared channel, we expect to reduce that, probably a factor of 2 or so, which means that then signals of the order of 2 or 2.5 meters per second would become visible in the time series.
As you have heard this morning, we're actively experimenting with laser frequency comm.
Oh, yeah.
Would there be any interest to adapt, let's say, after 3 years, an outcome of this research?
Of high interest, and Andreas will be discussing that. We have this strategy now that is working okay, because we have this stabilized Fabry-Perot etalon. The problem is that this is good for it. It's not an absolute reference as a frequency comm would be, and therefore we have to still use calibration lamps to set the nightly, let's say, level or nightly reference. And a laser frequency comm would completely solve that. So yes, I'd be thrilling to have a frequency comm.
It's time for one more question. Okay, let's thank the speaker
Okay,
again.
thank you.
The next speaker is Andreas Kurenbach, talking us on Carmenes and the future of Carmenes.
¿Perdón?
¿Algún cable tuyo?
Yo ya está, yo no tengo nada más.
Perfecto.
Estoy aquí. Aquí el USB, ¿no? ¿Quieres?
No, el USB, sí, este no lo esta es la conversación que va a tener con Dentro conectando a
There's David, but it's not working anymore. But here's the pointer from David.
Disculpa, esta es la ponencia que va a haber en Skype y
No, la siguiente.
Ah, vale.
Sí, 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 sí.
That doesn't work.
No.
Okay, does this have one?
So good afternoon. First of all, apologies for not being here for very long. I couldn't be here this morning, and I also have to leave again tonight. So I wanted to present some thoughts about what Carmenes could be in 2019 and beyond. So this talk is about some initial ideas about the science and possible upgrades that we could do. It doesn't discuss any of the financial or political aspects that this undoubtedly has. So you have just heard Carmenes 2016 to 2018. Carmenes is the first spectrograph that has been optimized for radial velocity measurements in the red and in the near infrared. Even the visible channel from Carmenes is different from HARPS and HARPS North in the wavelength coverage. So whereas HARPS and HARPS North, for instance, work mostly in the blue part of the spectrum, we work in the red part of the spectrum. That has advantages, especially, of course, for cool stars, but it also has disadvantages, namely we have to deal with an atmosphere that is much less benign, so we have to work a lot harder to eliminate the effect of tellurics, for instance. And the near-infrared channel is completely new, and in that sense, so Carmenes is a little bit of a trailblazer here. There are many other instruments that are under construction at the moment or planned for the future. Some of them at telescopes of comparable size, like Spirou and NIRPS, that are also at 3.5 meter class telescopes. There are a couple of instruments like HPF and IRS that are on 8 meter class telescopes. And of course, there is a design project to design a similar instrument, actually with multiple spectrographs combined in one instrument. Nope. No restart. And that is for the ESO 39 meter telescope. So there's a lot of interest by all these groups in the results and in the techniques that we are developing. And so we have to do the hard part. But of course, we are looking beyond what happens at the end of 2018, which is the period at Calar that is covered under the current operating agreement. And I'll touch upon 3 topics, namely our own M-dwarf radial velocity survey, then some thoughts about follow-up of transiting planets, and finally about a possible high-precision instrument upgrade. So first of all, the Carmenes M-dwarf survey that has been mentioned and or explained by Ignazi, that will have to extend beyond 2018. One reason is that we agreed to get 750 usable nights of GTO if the progress of the project is successful, and that is more than can be accommodated in 2016 to 2018. So we expect that the GTO will actually extend into 2019, 2020, so that at the end of maybe 2020, we will have finished our GTO observations and completed the 300 M-dwarf survey. But of course, one can also think about additional extensions and follow-up that go beyond our initial science goals. We had some specific science goals set out on which we based the calculation that we need this number of nights, as Ignazi explained, but there can be additional goals. For instance, intensive campaigns on the quietest stars to push the detection limits beyond our average of, say, 60 observations per star. This has been done. For instance, recently there was this announcement about a planet around Proxima where this had been done at HARPS. Or follow up on either the quietest stars or candidates for which 60 measurements or maybe 100 measurements are just not enough. You may also want to search for long period planets to address some interesting questions about planet formation. Because we don't know whether any M-dwarfs have something like Jupiter analogs. Also, one topic that is quite interesting, that is orbital dynamics in multiple systems. That needs long time spans of observations because the interactions between the planets are very telltale, with a lot of information about the architecture of the system, like mutual inclinations and all these things. But they need a long time base because the interaction between planets lead to changes of the orbital parameters that are detectable only over long time spans. And finally, one can think about looking at the long-term behavior of stellar activity. For instance, to search for activity cycles. We know very little about, say, dynamos of M-dwarfs and whether they have cycles. And there's a second thing that one can do if stars turn out to have cycles, you can look at the quietest periods when the variations induced by stellar activity are smallest and use those periods to look for low mass planets that during more active phases in the activity cycle are hidden by the stellar activity. There's also potential for follow-up of our survey, namely studies of planetary atmospheres. High-resolution spectroscopy is a great tool to characterize planetary atmospheres that has been demonstrated by the Leiden group, Ignaz Snellen and others with the CRIRUS instrument at ESO, and it has been demonstrated with HARPS. So we are certainly trying at the moment to do the same thing with CARMEN-S. There are some pilot programs exploring how well this works, and there are some interesting spectral features in the wavelength range that we cover. We don't cover the K-band, which is used for most of the studies that have been published on this topic, but there are interesting spectral features in the wavelength range that we do cover. And certainly we expect a few transiting planets that will come from our survey, but one doesn't need transiting planets. The method works also with non-transiting planets. So here is a figure from an article that appeared in the ESO Messenger explaining how this works. In essence, you have a star, and in this case, a transiting planet going around the star. And if you take the spectral lines of the planet, the orbital velocity of the planet is very large. So with time, the spectral lines move through the stationary spectrum of the telluric lines, and the stellar spectrum is also almost stationary because the star, of course, has a much, much smaller radial velocity. But the amplitude of the planetary lines are very large, and you can either look at them during the transit, if the planet is transiting, or you can also look at them in emission close, so when you see the day side of the planet, so you don't need a transiting planet to do that. And there are techniques to combine the information from many lines in cross-correlation techniques and so on that make this method quite attractive. So that brings me to the more general topic of follow-up of transiting planets with CARMEN-S. So here one should take a look first at the transit survey landscape. There are a number of space missions, 2 in the past, Corot and Kepler, 1 currently going on, K2, which is the same hardware as Kepler, but a different mission scenario. And then there's TESS and Plato that will be in the coming couple of decades. So very well matched, or very well suited for a discussion of what should go on Calar Alto in the years 2019 and following that, perhaps up into the 2030s. There are also many ground-based surveys, and I just mention M-Earth and Speculoos because they deal specifically with M-type stars, but of course there are many other ground-based surveys of transits. So there are lots of these surveys providing transiting planets, and there's a need for massive follow-up. They are taking, for instance, one example that is now coming close. The TESS satellite will be launched in 2018 and do a full sky survey. And in a sense, this mission is very complementary to CARMEN-S if you think about the task of characterizing the solar neighborhood. As Ignazi showed, the mean distance of our targets is 13 parsecs. So what CARMEN-S does is we really look in the solar neighborhood for our nearest neighboring planets. And so the CARMEN-S detections in the end should be most of the most nearby planets. And what TESS will give us by doing a full sky survey is the most nearby transiting planets. So that's a different sample, with overlap, but so these samples will be the most nearby objects of a specific type. One is planets and the other one is transiting planets. The way TESS works, and there will be a presentation on that, so I'm not going to say a lot of that about that. It is very well adapted to finding planets with a period that corresponds to the habitable zones of M dwarfs. And it will, because it does a full sky survey and gives the brightest of the transiting planets, provide many with a J magnitude that is brighter than about 10. So this will be a very rich source of targets that can be followed up, and there's a need for a really large-scale follow-up program for TESS. Why do you want to do that? First of all, it's the simple point of confirmation. You want to eliminate false positives, and although we have learned a lot from missions like Kepler how to do that from the transiting data alone, the best confirmation that you really have a planet and not some weird false positive is still detecting the planet also in radial velocity to confirm the existence of the planet. The second point is extremely important, and that is that the transit plus the radial velocity gives you the radius and the mass of the planet and therefore the density. This is very explicitly the main goal of the Plato mission, ESA's flagship exoplanet mission to be launched in 2024, where this is really called out as an essential part of the mission, and of course it's also very important for the science that will come out of TESS. And finally, there's the transit spectroscopy that gives you atmospheric structure, information on the chemical composition of the atmosphere, and even things like winds, from which you can learn about the energy transport in the planet. And, I take this diagram here that shows here the mass in Earth masses, and here the radius of known transiting planets. And so populating this diagram, pushing down to one Earth mass, is a very important scientific goal for both TESS and Kepler, but it can only be achieved with radial velocity follow-up. And you see that in many cases where you have very nicely determined radii, the error bar on the mass is still very large. So the radial velocity part is actually quite challenging. And you need very good measurements of both the radius and the mass of the planet to be able to place it on a diagram and determine what the composition is. So going from 100% iron, which is probably the most dense that we can imagine as reasonable for our planet, through something that is rocky as we know it from our Earth, somewhere in this region, to planets that have a lot of water, and then above here planets that have a gaseous atmosphere. And so even determining at one given mass, or one, you can also start with the radius at one. If you have one of them, you have no idea really whether what you are looking at is more like a Neptune or more like Earth. So why would you want to use Carmenes for this? First of all, Carmenes is optimized for red stars, so it's an excellent match to the science of TESS, and also very good for Plato science, because many of the targets are very red. It has a wide spectral coverage, including very important atomic and molecular lines, which makes good potential for transit spectroscopy. And this is all about getting large sample sizes to learn about planet formation and statistics in our neighborhood. So there's a need for a big team effort, and would be a very nice key program for CAHA. So finally, I would like to present a few ideas about potential high precision instrument upgrade for Carmenes. So here we have to get clear about what Carmenes is and what it is not. So Carmenes was designed to be the best spectrograph for RV monitoring of mid-M dwarfs. That is the one design goal that we designed the instrument to. And as a consequence, Carmenes provides a large wavelength range, because we wanted to have access to activity indicators and because we wanted to be able to measure RV as a function of wavelength. And we can access terrestrial planets around M dwarfs. So this is what we have at the moment. What CARMENES is not, CARMENES was not designed to be the most stable spectrograph in the world. So we never ever said that CARMENES would be as good as HARPS, for instance, to do radial velocity measurements. Or we never said we wanted to compete with instruments like Espresso or the new instruments that NASA is funding. And the simple reason is that the requirements were already tough. Remember, we are going into a wavelength range in which radial velocity have never been measured before very precisely. So our first goal was deal with that problem and not try to beat other instruments in the blue where it is easier and let them do the very high precision. We'll go for red sensitivity. So this has been covered by Ignacy. We have wide wavelength coverage. We have demonstrated that we can do 2 meters per second, at least in the visible. And in the near IR, this is very challenging. And to get to 1 meter per second, we really need probably the coming years to actually get there. But there's certainly the potential for upgrading the instrument and push into the sub-meter per second regime. Precision something like 10 to 30 centimeters per second. An obvious reason for wanting to do that is to look for lower mass planets for the brighter targets of CARMENES. Of course, you also need more photons, so that would mean we would have to pick the brighter of our target stars. There's an additional very interesting scientific driver, namely terrestrial planets around G and K stars. So as a benchmark, the Sun, the Earth around the Sun induces a radial velocity variation of 9 centimeters per second. So to detect a true Earth analog, you need a radial velocity precision of at least 10 centimeters per second. This, of course, has very, very high scientific interest. It would be an extension of the ongoing survey towards earlier spectral types, and it would potentially be a target finder for multi-billion-dollar missions that are currently on the drawing board. For instance, at NASA, NASA is discussing HABEX and LUVOIR, two architectures for missions to characterize Earth-like planets, in which hopefully Europe will participate. And so finding targets for these would be very important. So I took a slide from Maggie Turnbull, who presented this to the HABEX working group, and she has something like the Super 7 stars in the solar neighborhood. Perhaps the best targets to look for Earth analogs. There are stars like well-known stars like Tau Ceti, Epsilon Indi, Epsilon Eridani, the Alpha Centauri system, and so on. And out of that 7, 4 are in principle accessible to CARMENES. So they are in the north, and they are not A-type stars like Sirius. So in principle, we can look at a fair number of these very prominent stars in the solar neighborhood. And why would you want to do that with CARMENES? And one of the important reasons is that if you want to push into this regime below 1 meter per second, even for sun-like stars, the RV uncertainty, or the noise, quote-unquote, on the RV is dominated by stellar noise. It's the star spots, it's the plage that creates RV variations that are difficult to overcome. And this is the limit that all these radial velocity surveys will be running into. Even if you have an ultra-stable instrument like Espresso, the stellar noise is the real problem. But CARMENES is the instrument that is optimized. It has been optimized to deal with this problem. Unlike any of the other existing instruments, means it works in the red and in the near IR, where stellar noise is less than in the blue. It has the wide wavelength range to actually try to disentangle planets and stellar noise. So in a way, this architecture of CARMENES may turn out, I hope it will turn out to be the key step forward in pushing radial velocities to a regime where other instruments cannot go, not because of instrumental reasons, but because of the stellar noise reason. And actually, a 3.5 meter telescope is sufficient for nearby stars. If you take the sun and put it at 10 parsecs, it will have an I magnitude of 4 or a J magnitude of 3.5. So that would be a G25 star at 10 parsecs is doable. Of course, you need very many observations per star, and again, this would make a nice key program for CAHA. You cannot possibly do this with an ELT, and probably also very difficult to do at 8 meter class telescopes. What would be needed? We would have to improve the thermal stability, so we would have to upgrade our temperature control systems. We would probably need improved guiding stability, maybe a tip-tilt mirror in the front end, which we don't have at the moment. We would certainly need improved calibration stability, so a laser frequency comm would solve that. And we would have to work on our data reduction pipelines. For instance, more advanced ways of treating tellurics, sophisticated ways of analyzing activity indicators, correlating activity indicators with RVs, correcting RVs from their wavelength behavior, and so on. So this is all currently we are starting a discussion, so to speak, about the technical possibilities that we have, but this is a possible scenario about what Carmenes could do beyond 2018. For the main possible scientific things. Of course, it is also a great instrument for a lot of other topics in stellar astrophysics because it provides this very nice large wavelength coverage at high resolution that no other instrument has that's currently even on the drawing board, except perhaps for the HIRIS instrument at the ELT, which will not come for another at least 10 or 12 years. So, thanks a lot.
Comments or questions?
Andreas, thanks for the talk. The laser frequency comm, or you say, or any advanced lock data, what do you mean, how much do you expect this device adapted will improve the final product? How much, which proportion, a figure of merit from that?
Okay. Yeah. If you want to push substantially beyond 1 meter per second, down to 30 centimeters per second, 10 centimeters per second, you have to work on all aspects. Yeah, there's not a single thing anymore that limits your precision. You have to push everything. And of course, one thing is the long-term stability, which currently our long-term stability hinges on the hollow cathode lamps, and we know that they have a life. They grow old, and the line ratios change, and people have come up with relatively complex schemes of trying to calibrate different lamps against each other and so on, but there's no absolute solid wavelength reference that is better than 1 meter per second coming from these hollow cathode lamps. So that is a pretty fundamental limitation, and the best known way to solve that is laser frequency comms. It's the best way, but also currently at least an expensive way. There are various R&D efforts to make laser comms more affordable, but certainly on the scale of such instruments, even today, laser frequency comms are an expense that is not completely outrageous. So currently, we would have to add a couple of million or so on the budget of Carmenes, which was significantly enough so that we couldn't do it, but it's not a factor that would dominate the budget.
No questions?
And they could become much cheaper.
Calar Alto organization or structure of the observatory would allow sharing laser comm not only between different instruments, but also between different telescopes. We could share only one source for 2 telescopes, for several different instruments.
Thank the speaker again. And the last talk in this session is on the test mission by George Ricker
George, can you hear me? George? You have your sound, your microphone on? George, can you say something? Okay. No, pero mira que él va a salir por...
No hay ningún problema. Lo vamos a... No pasa nada, no pasa nada.
Sorry?
No pasa nada.
George?
That working? Is the audio open?
Yes, everybody's listening to you. So you are in the air, you can start when you want.
Well, thank you very much. If it's possible to hear me, I'd like to say that I'm very pleased to join the meeting by WebEx, although I wish I could be with you in person in Granada. So I'll be describing the arrangements for tests, and just a moment, I'll go to full screen. Just a moment here. Okay, can you see my full slide now? Yes. Good, thank you very much. I'll be describing the test mission today, and Sarah Seeger will actually be joining me for the questions portion. So when at the very end, when we talk about some of the science program, she may be able to assist as well. Some of the material that I'm going to be presented has been prepared by Zach Berta Thompson and by Peter Sullivan, so I'd like to credit them for some of the figures that I'll be using. TESS, as you may know, is a NASA Explorer mission, and it's scheduled for a launch in 2017. And the basic plan is to explore the solar neighborhood for small exoplanets that will be amenable to detailed characterization, both near-term and long-term. In that sense, TESS is a bridge to the future that actually allows us to go from the predecessor measurements that have been made by Hubble, Spitzer, and Kepler, and especially by Kepler, and to prepare the way for observations with JWST and for future missions such as HABEX and LUVOIR that have been discussed and are still in a very early stage of formulation. The way in which TESS actually has a relationship directly to JWST from the point of view of space missions is that it will actually act essentially as a finder scope. It'll provide locations and the first steps toward characterization of the exoplanets that will be of interest in the future. I'd like to show you a short animation. I hope this will come through okay on WebEx that actually shows the significance of exploring the solar neighborhood. In this plot that I hope you can see, the sun is at the center and right ascension is in a ring. This is basically a projection down onto the equator. And as the projection will run, you'll see dots that indicate by their color whether they're from Kepler, radial velocity, which would be the bluish purple spots, and the orange ones, the pinkish orange ones, will be from TESS. And if the star has 5 corners, that would indicate that it's potentially habitable. So if I actually let this run, then one of the things that I think you'll see as we move out to something like 3 to 5 parsecs, this simulation predicts that TESS could conceivably see a habitable zone planet with a temperature of 237 Kelvin that's comparable in size to the Earth. And as you move further and further out, you see that other planets, other stars come in with potentially with transiting planets. And so we're out now to about 10 parsecs. And if I move further out to about 100 parsecs, then you can see that the population of TESS identified planets should be quite dense. And then you can also see that there's this spray of transiting planets that's coming in from the upper left-hand corner of your screen that are in gray and black, and those are the ones that correspond to Kepler. And as you go further and further out, then you can see the impact of 100 square degrees that was thoroughly studied by the Kepler primary mission. So in comparison to Kepler, it's important to realize that TESS has really been optimized for far red to near infrared observations. The solid black line shows the spectral response for the TESS system, both the lenses, the filters, and the CCDs themselves, which are a deep depletion structure. And in comparison to Kepler, it's quite a bit redder in terms of its overall response by design. I'd like to just spend a couple of minutes before I talk about some of the things that TESS is expected to find, giving you a brief update on where the TESS hardware actually stands. This is an image of the TESS focal plane, at least one of the four, during its final inspection. This is actually flight hardware, which we've been in the process of checking out for the last couple of months. The first focal plane array with 4 of the TESS CCDs is currently in test at MIT. In fact, we've actually moved on now to the 3rd focal plane that we're actually testing. This is a structure that you can see the operator holding here is the focal plane itself, and then below the operator's right hand, you can see the flight electronics that's just below this. This is as it was being inserted into a vacuum chamber to do full characterization of the CCDs and to do flat field testing. The lenses for TESS are special lenses that are being currently assembled into the cameras. There's going to be a total of 4 such cameras, and that's important in terms of the way that TESS's observing strategy is arranged. This is actually the first flight lens that was completed undergoing its final assembly and interferometry tests at MIT about 1 month ago. The sky mapping plan for TESS is an important part of the mission. The set of blue bars that you see on the left-hand side of your screen, extending 96 degrees up, down, and 24 degrees crosswise, are the fields of view that are combined for the 4 TESS cameras. And then the globe that you see on the right actually shows the projection of those fields of view onto the sky in ecliptic coordinates. So as you can see, there's in ecliptic latitude, the field of view extends from 6 degrees up to over the ecliptic pole, and in fact the 4th camera actually is centered on the ecliptic pole. And as a result of the way in which the array is configured, we have varying observation times depending on the location within the sky, and they range from almost a full year in the region around the ecliptic pole to a shorter period of time of 27 days as you move down toward the ecliptic itself. Now, the other thing that I'd like to share with you is an attempt to give us an appreciation for how large the field of view of TESS actually is. This is a field of view of a single camera, 24 degrees on a side, and the 4 sub-panels correspond to the mapping of a single CCD. So the blue outline is for a single CCD, And just for scale, the little green box in the lower left-hand corner corresponds to a 1 degree field of view. So this simulation actually shows what we expect to see from an actual catalog, and it shows things like there's a small cluster of stars, there are defects, there's shadowing from obscuration within the galaxy that's also shown in this. Now, as you then say, what else can we do with these images? One important thing is that TESS has actually 2 ways in which the data is actually being recorded and transmitted to the ground. One is to use postage stamps, so-called imagettes. That was another phrase for it, which was the method that Kepler adopted. But the other thing that we're able to do, because of the unique orbit that TESS is in, is we can actually bring down full-frame images. This means that every single star, every single galaxy, down to the limiting magnitude of the survey, is transmitted to ground every 30 minutes. And that means that down to the useful photometric limit of 1%, there should be about 30 million objects, approximately 20 million stars and 10 million galaxies that would be accessible for TESS. When we then simulate what TESS should be able to detect in ecliptic coordinates, which is what this slide shows, you can see the clustering of the red dots, which are the detectable planets around these 200 pre-selected stars for which we'll have imagettes. Those are going to be clustered around the ecliptic poles, the north and south ecliptic poles, as you can see. And then, in addition, there are detectable planets around the 20 million stars in full-frame images that are shown in these faint blue dots. And you can see the region right along the ecliptic equator where TESS does not observe in its primary mission. And you can also see the region of confusion extending from the lower left across the ecliptic up toward the north pole, the north ecliptic pole, where the galaxy is actually located, the plane of the galaxy where the star density is so high. For scale, this is the Kepler field as representation. The yield that we anticipate for TESS is shown in this next plot. Note that this is a log scale on the y-axis, and the 4 bars that are shown in the histogram give the distribution in expected planet sizes that we will have for the full-frame images in blue and the pre-targeted stars for the postage stamps in red. And what you can see from this is that we anticipate that we'll find about 500 planets that are going to be smaller than 2 Earth radius. And these are the ones that are, of course, of most interest. Many of these will be M dwarfs. In fact, the vast majority will be. And those are the ones for which mass measurements can be used to resolve whether the planets are rocky or not. And then the other will occur, of course, is for still small relatively small planets, but including sub-Neptunes and water worlds. We anticipate something like 1,500 planets. Now, these are going to be important for atmospheric studies by missions to come, including especially JWST. And then finally, there's going to be something like 17,000 distant giant planets that will be found in the full-frame images, and those are going to be of interest for evolutionary studies of giant planets in the future. The other thing that we've talked about for this, and then when Sarah is joining us at the very end for questions, we can talk about this part of the program a little bit more, is we have formulated a plan for small planet validation and mass measurements. And this funnel diagram, as we refer to it, actually describes how this process works. So at the top of the funnel, we introduce the light curves from the 200,000 stars. Now, this particular diagram only covers what is contemplated initially for the full frame, for the postage stamps. And there are also objects that are coming into this program from the full frame images. That's another issue. So we anticipate that we should detect about 3,000 transit-like signals in the initial survey. Now, and this is in the form of spacecraft data that would be delivered to the archive at Space Telescope in 4 months of its acquisition. And the initial delivery will be 6 months because of the startup time for that activity, but subsequent deliveries will all be for 4 months. And then that initial data will undergo screening by natural seeing observations and adaptive optic imaging. And to that purpose, we have made definitive arrangements with a number of ground-based facilities that have actually committed to the mission to make these observations in real time for screening, or as close to real time as can be achieved. And of those, so the fallout from those initial events is expected to be fairly low. The initial estimates that we've made from the use of the Kepler pipeline as modified for tests is that about 2,500 out of the 3,000 will survive this screening. And then when the reconnaissance spectroscopy is carried out largely through the use of the LCOGT, the Los Cumbres Global Telescope Array, we expect something like half of them, a little bit more than half, that would survive that stuff. And then of those, about 6% would be selected by the science team for precise radio velocity follow-up. And what that means, and then because based on the requirements that NASA has placed on the mission, those are going to be the ones which will constitute the 50 measured masses that in NASA parlance are considered to be the mission's level 1 requirements. But that will also mean that 94% of the small planet candidates are going to be available for community precision radio velocity follow-up. So that's an important factor to keep in mind for tests, is that there's going to be a wealth of candidates that are going to be available for both immediate and future follow-up. For the timeline on the mission itself, which is shown in this next diagram, we're right now in the phase of the program in which we have the flight hardware coming in, the software for the flight system is being developed, as well as the ground system. And then we're also about to undergo the period of observatory integration with the spacecraft. The launch is currently scheduled for the end of 2017. We would then have a commissioning phase period of about 2 months, and then the survey of the first portion of the sky, which will be the southern ecliptic hemisphere, would start in March of 2018 and continue for a year, and then the northern ecliptic hemisphere would be observed in the second year, starting in March of 2019. And the mission is nominally for 2 years, but the basis for the orbit, the spacecraft, and the resources that are needed can certainly support an extended mission going much longer. The orbit should be valid for decades, and there's also no intent on in any of the other resources within the satellite that would last less than 5 to 10 years. So we anticipate that there will be an opportunity for an extended mission to last into the period of time that future missions like Plato will come online. So these are the summary items that I'd like to leave you with, that the mission is really dedicated to finding nearby small transiting planets. We are on schedule with the instrument and the spacecraft to launch in late 2017, and the goal for TESS is to identify the best small planet targets for radio velocity measurements of mass and atmospheric characterization for for the community as a whole for the duration of the mission and many decades beyond. So thank you very much, and if you have questions, I'd be happy to take them now.
Okay, thank you. We have time for a few questions.
I'm sorry, I could not hear the question, so if someone could repeat it, that would be...
No questions yet.
Okay, thank you.
No questions?
What is the role that Alto can play?
We have an amplifier.
This is Jose. I will repeat the question. What is the role of Calar Alto in this science topic?
The role of Calar Alto should be very important because of the fact that many of the best candidates that we're expecting to see will be M dwarfs. The number of facilities, the alternate facilities which are optimized to do infrared spectroscopy that we're aware of is very small, and Calar Alto is the premier facility for this type of work. So we've been very pleased at the progress that's been made with Carmenes, and it's our hope that that facility can continue to be available both during the primary test mission as well as during the extended mission.
Okay, more questions?
So, can you tell us a bit more about the magnitude distribution of the targets that you expect?
Magnitude distribution of the targets that you expect.
Yes, the calculations that are shown from these simulations are based on the assumption that TESS, which has a natural I magnitude of about 12, we've assumed the known star distribution down to magnitude I of 12, and for M dwarfs we've gone down to about 13th magnitude. And as you can see from the way the distribution is arranged, and I didn't actually talk about the photometric precision, but the photometric precision is expected to be comparable to that of Kepler. So it should be in the range 20 to 60 parts per million. For the transit depth that we anticipate for many of the candidates, they'll be in the range of 200 to 500 parts per million. So these should be very good targets for Carmenes.
One more question.
George, what is the plan for the extended mission? Has this been finalized?
Plan for extended mission.
No.
Okay.
Yes, the extended mission is determined by NASA once the primary mission is in operation, and it's actually established in terms of the duration and conditions for the program by a process that NASA calls the senior reviews. These occur every 2 years. The next one would be in 2018, which would be during the test primary mission, so we would probably not formally be considered in that. The one that we would be considered in would be 2020. So I think that what's likely is that there would be some sort of a preliminary assessment that would be made, or a tentative extension of the mission that would occur of the review of our operations during the primary mission in 2018 and 2019. And then if the mission succeeds, then in that review, then we would go for the likely extension would be for 4 years, but with a firm extension of 2 years at first. One other consideration is that the way that that NASA is also viewing this program is that, unlike many missions, unlike Kepler, for example, there's been a guest investigator program that's been established even prior to launch, and as a result, there will be an opportunity for the proposal of targets by the community itself before the mission actually launches. There's some of the 200,000 candidates that we're going to be assigning postage stamps to. There's an allocation for an additional 10% of those to be provided by the community, or an additional 20,000.
Okay, many thanks to George and all the other speakers in this session.
George, please stay on the line.
And now let's go for coffee and come back at 5:25.
Thank you very much.
So picture is at the end of the coffee break.